Hey, it's Warner, and this is the 2008 AP Physics C Mechanics question number 2. We have a horizontal uniform rod, so you see that right here. Has a length of 0.6 meters, has a mass of 2 kilograms. The left end is attached to a hinge that is frictionless. The right end is attached to a spring scale that can measure the force at an angle of 30 degrees. And then we have, right here, we have a box or a crate or something. Block has a mass of 0.5 kilograms. So the thing that they want us to do first is go through and draw and label vectors to show the forces that are acting on the rod. So our very first one that we need to draw, I would go ahead and let's just draw one right here, pointing straight down, and this is the mass of the box times gravity. In the middle of the rod is the mass of the rod times gravity. And then we have a tension force that we're going to put here. And then the last one is the force of the hinge on this rod. Now, because this makes a 90-degree angle right here, we know that the hinge is not taking, the hinge is acting as part of the support system for it. But what's holding the hinge is this rod. So when you do this, you have to think about the vector sum of both. So the hinge, if it was only holding it and there was an equal and opposite force just in the x direction, then this really wouldn't work out very well. So it's got to be in the up and down direction too. If you didn't have anything in the up and down direction, this would just slide and fall down. So the last one is the force of the hinge. And so I'm going to call it FH. And it is just the sum of the two kind of pointing off in this direction. And remember, it's because you do have to have something both in the x direction to keep it from sliding and in the y direction. Okay, so next thing they want us to do is go through and they want us to calculate the reading on the spring scale. Let's go back up for just a second though. You get 1 point for each one of these. So those are the 4 points that you would end up with that. Which is really kind of nice, being able to get 4 points for not doing much. So we need to show that the sum of the torques of this system are all equal to 0. The other thing that we need to do is we need to figure out what is the equation for each one of the torques that are on this system. So probably the easiest thing to do is, since we know all the torques here, let's go through and do anything that's moving in a counterclockwise orientation. So the one that is moving in a counterclockwise orientation is Ft. So here I'm going to say that that is Ft times the length of the rod, or we can just put R. And that one is positive. Everything else is going to be negative. So that's going to be minus the mass of that box times gravity times its position, minus mrg for that rod times its position. And so we're going to call this one the radius to the box, the radius to the center of the rod. And then finally, we have our h. And we notice that about the center of this thing, it's also going clockwise. So we're going to say minus fh. And then we need to kind of think about what it is doing in terms of its torque. So if we think about everything rotating about this point right here, notice that the hinge doesn't have any distance. So that's going to be 0, which means we can just ignore the hinge. The hinge is just holding it up. It's not doing anything else other than providing a point for it to rotate. And because of that, those are all equal to 0. So that makes it a lot easier to go through and do. Okay, we know that we have a 30-degree angle here, so we can't just do Ft. We've got to think about the what's going in the direction of motion. So because this, we could have it go up or down, it's in the y direction that we want that motion. So this is going to be the force of tension times, and then here we're going to do the sine of 30 degrees, because that would be this side of the triangle, which is the one pointing in the direction of motion, which is up and down. And then we need to multiply that times the distance that it is at. And so the distance that that very end is at is 0.6 meters. So we're going to put that 0.6 in here. Minus the mass of the box times gravity. And we know that the mass of the box here is equal to 0.5. So we're going to put 0.5 times 10. And we're going to then have to multiply that times 0.6. And then finally we have the mass of the rod, which we said was 2 kilograms. We know that's times 10. And then it has a length of 0.6 meters, but we want it at the center of mass. So that should be 0.3. Okay, so all of that is equal to 0. And they want us to find out what is the force of tension. So here we're going to go force of tension is equal to, so we're going to move these two things to the other side. That's 1/2 of 10 times 0.6 minus, and then we have plus, because we put it on the other side, 2 times 10 times 0.3. And then we're going to divide all of that by the sine of 30 times 0.6, or 0.6 sine of 30. So let's do that math, see what we get. And so when you do all that math, you should end up with 30 newtons for the force of tension that is in that spring scale. Where do we get points for this? Well, I've done this one a little bit differently than they have on the AP website, which is good because I think this is a lot easier to do. You can take a look at the answer or the solution on AP Central and you'll kind of see what I mean. You really have to have sum of the torques is equal to 0. If you don't do that, you will not get that point. Second point is for having the equation where you have all the variables shown. And then after that, it's basically just giving you points for plugging everything in and then having the right number answer with the right unit. So far we've gone through and we've earned 8 points on this. The next thing they want us to do is they say the rotational inertia about the rod center is 1/12 ml squared. And they want us to find the rotational inertia of the block system about the hinge. So obviously for this one, we're going to need to use our good friend Pat, the parallel axis theorem. We know that the total for this rod, it should be equal to I of the rod plus I of that box. So when I find the moment of inertia for the rod, that's going to be equal to the center of mass for the rod plus ml squared. That's equal to, they already told us that about its center is 1/12. So this is 1/12 ml squared. And to that we're going to add plus, now let's go ahead and make this look more like this. Now we also need to put in our ml squared here, but we want to be careful because this is really going to be 1/2 of, well, it's not really that. Here, let's do this. It should be your mass of your rod times the length over 2, because we know this is to that point from our hinge over to the center. So this is squared. Okay. Now that we've done that, we need to go ahead and combine everything that we can combine. And so if you do that, we're going to get 4/12 times ml squared, which is equal to 1/3 ml squared. So that is just for the rod. We also need to go through and kind of think about the hanging block. And so for the hanging block, I for that hanging block is equal to just ml squared. So that was pretty easy to do. Now we're going to add the two together, and so our I total will be equal to 1/3 ml squared plus, and then here we're going to have the mass of the block. So let's put MB in here. Mass of the block times L squared. And let's go ahead and plug everything in now. So here we've got 1/3 of the mass of the rod times its length, which is 0.6. And you know what? I don't think we put the total in here correctly. Nope, we did. We're set. So we've got 1/3 times 2 times 0.6 squared plus, And then we have 0.5 kilograms times 0.6, and this is for that block squared. So that is going to be equal to 0.42 kilograms times a meter squared. And so that would be your total moment of inertia. It says if the cord that supports the rod is cut near the end of the rod, calculate the initial angular acceleration of the rod block system about the hinge. So as long as you have the moment of inertia right, this should be pretty easy to do. Oh, you know what? Let's go back and just make sure that we know where all of our points come from in that previous spot. So there are 3 points here. One of the points is for just recognizing that you're going to need to add the moment of inertia of both together. One of them is for using the parallel axis theorem to make sure you get this, and then one is for just finishing everything out. Okay, so let's go ahead and move on down to letter D, and for letter D, they want us to try to figure out what that angular acceleration is. Always, always, always with these, always say the sum of the torques are going to be equal to I times alpha. We know the sum of the torques is mgl plus mgl over 2, and that is equal to I times alpha. At this point we need to solve for alpha, so alpha is, if we go through and do our math, we can factor out g and l. Okay, we're going to divide by I, and then because we factored that out, what's left on the inside is the mass of the block plus the mass of that rod divided by 2. So now what we're able to do is go ahead and solve. So alpha is equal to 10 times 0.6, and we're going to divide that by the 0.42 that we got earlier. And to that we need to multiply the mass of the block, which is 0.5, plus the mass of the rod, which is 2, and we're going to divide it by 2. And so now we're going to end up with 21 radians per second squared. So points for this one, definitely for here. You also get a point for making sure you've plugged everything into it correctly in terms of just kind of fleshing it out and then going through and solving. So that's 14 points. Your extra point is for units throughout. And that would be your 15th point. And that is the end of this super easy, much shorter problem.